Okay, so this is a great pleasure to have on our seminar Xavier Pérez-Giménez. Today he will have a talk about the chromatic number of a random lift of KD and regular graphs, and this is the same topic as on the conference, but I hope so that today we will have more details.
Okay, well, thanks, Maxim, for the introduction. And thank you, everybody, for attending it. Yeah, like there are not too many people, but I imagine like it's 7 p.m. in Moscow, so the time difference, yeah, like plays a big role. So appreciate everybody for coming. Indeed, I'm going to talk about the same topic as in the conference. I was wanting to talk about something else, but this has been a stressful semester, and I didn't have time to get around to make new slides. Yeah, so if you have already listened to a version of this talk, well, and you can ask more questions. Yeah, so I'm going to talk about some work that we did with a student at UNL, J.D. Neer. He's now at the University of Manitoba in Canada. And we've been very slow at writing down the article, but if anyone wants to read that, that appears in his thesis. So I can send you a link to that. So I'll just move your faces to the side. Okay. So the notion of a covering map arises from topology. And if you don't know any topology, that's okay, because I don't know any topology either. So I'm just going to explain what this means in the context of graph theory. So in the context of graph theory, a covering map is a graph homomorphism between two graphs, L and G, which is surjective. And it's a local bijection in the following sense. So yeah, it's a bijection between the set of edges that are incident with a vertex and the set of edges that are incident with the image of that vertex. And that's, well, I'll give an example in a second. And whenever we have a covering map from a graph L to a graph G, we say that L is a lift of G. So we'll call G the base graph and L the lift whenever we have such a covering map. So here's an example of a lift of this base graph here. I'm just, each of these bins, which we're going to call fibers, are the pre-images of each of these vertices in the base graph. So yeah, so each fiber contains all the pre-images of any of the vertices in the base graph. As you can see, well, all the fibers contain the same number of vertices, and in fact, for each two fibers that correspond to adjacent vertices in the base graph, I have a perfect matching. So that's what lifts look like, and well, let's verify indeed it's a surjective homomorphism, and also you can see the local bijection very easily. So between, yeah, like there's a clear bijection between the set of edges incident with this vertex and its image. Okay, so this definition can be extended. You have to change the definition a little bit for it to make sense, but well, to base graphs that have loops and multiple edges don't pose a big problem. So if you have a repeated edge here, basically there's going to be another perfect matching between these two fibers. So multiple edges don't require to change the definition a lot, but there's a way to generalize that to allow loops. I'm not going to get into the details or what the exact definition is for loops, but I'm just going to tell you what things look like. So if you have a loop, I'll just place it somewhere else here on the base graph. what this corresponds on the left, you're going to have, well, in the corresponding fiber, you're going to have a two-factor, which could be this cycle here, or it could be, it's also a two-factor. There's also a notion of half loop, which you can think of, it's like, looks like this, like a pendant edge that, it's like a loop that only contributes 1 to the degree, while like normal loops contribute 2 to the degree, so half loop contributes only 1. And the right, yeah, like the right interpretation of what this is on the left, that would be a one factor. So a perfect matching, or sometimes you can have also some vertices here with a half loop. There's an algebraic definition that includes all these situations, and also for directed versions of this model. But I think I just want to stick to this visual idea of what a lift of a graph looks like. And I won't be talking about loops and half loops much, but I just wanted to let you know that they exist. Okay, so as I said, well, so here's an easy observation. If my base graph is connected, then all the fibers have the same cardinality, as I mentioned before, which could be infinite. So in fact, there's a notion of universal lift, which it's an infinite tree that is a lift of a connected graph and that has some universality property, but I'm gonna focus on finite graphs only. So if I look at a finite lift of a connected graph, all the fibers will have the same cardinality, which will be, I'm going to denote by n. But so this motivates the definition of an n lift. So an n lift of a graph is a lift where all the fibers have the same cardinality n. So of course, if G was not connected, then you can have lifts where different fibers have different cardinalities, but you can also define an n lift. So you can always restrict your attention to lifts where all the fibers have cardinality n. So we're going to be looking at n lifts of a fixed base graph. So here's some easy facts. If my base graph is deregular, so is any lift. In fact, the degrees are preserved in the following way. So if I have a vertex here that has degree 3, all the vertices in the corresponding fiber, because of this local isomorphism of the set of incident edges, all the vertices in the fiber will have degree 3. And this vertex has degree 2, and all the vertices in the corresponding fiber have degree 2. So in particular, if G is deregular, so is the any lift L. And as I said before, loops contribute to the degree with 2, and half loops contribute with 1, but whatever they are. A third easy fact is that the chromatic number can only go down if I take the lift of a graph. So here I have a proper coloring of this graph G. It's not optimal. You could do with fewer colors, but the lift inherits. So if I had a 4 coloring, I can easily create a 4 coloring of the lift by giving to each fiber the same color as in the base graph, and that gives me still a proper coloring. So if I can color G with its chromatic number of colors, then I can do that for L as well, but maybe I could do that with fewer colors. Okay, so that's something good to keep in mind since we'll be interested in precisely this graph invariant. Any questions so far about what a lift of a graph is?
It looks almost like the L is like disjoint copies of G. Is that correct or no?
No, it could be.
Okay.
So maybe let's think of an easier, yeah, like, so certainly if you have these joint copies of G, that's a valid lift. But for instance, I don't know. Yeah, like if G is this
picture,
triangle,
right?
sorry?
In the picture, it almost looks like that. Just because the diagram, I can't.
Okay, well, I hope it's not.
Okay, okay, okay. No
Well,
problem.
Yeah. Oh, no, it's not.
No, no, no. It looks like two of them are together and one of them is. Okay, that's okay.
Yeah,
Thank
yeah.
you.
So probably the picture, yeah, there's one component that looks like G
Correct.
and
Yeah,
the
yeah,
other
yeah.
one isn't.
Okay.
But yeah, no, that's a good point.
It almost looked like all three were, but I guess not. Okay.
Okay, well, that's a good point. Okay, so so then since I'm a random graph person, then it makes sense to consider well, a random model for this kind of graph. So you can build a random n-lift by just, well, choosing one uniformly at random. So one way to do that, and so this was introduced by Amit and Linial, and so there are a number of papers by Amit, Linial, and Matuszek that they look at this model and they look at different graph invariants for this model. Yeah, like I think there are other papers by statistical physicists that also look at random lift. So yeah, other people have looked at that too, but I think it was introduced in these terms by Amit and Linial. So you can build a uniform random n-lift of a fixed base graph by first replacing each vertex by a fiber with n vertices, and then throwing a random perfect matching between any two fibers that correspond to adjacent vertices. And you can do that, well, all the perfect matchings are uniformly chosen and independently. And you can adapt the model also to incorporate loops or half loops, but here you might decide if you want to condition on simple graphs or not. And so you could, yeah, like you could throw random, if you had a loop here, you could throw random two factors, but then you might want to decide if you want to condition on simple graphs or not. Okay, so, but then in particular, so if, let's say your base graph G is 6 regular or the regular in general, depending on what G you pick, you get a different model of random 6 regular graphs. So you could pick the K7, or you could pick a bouquet with 3 loops, or you could pick the complete bipartite graph K66. And if you build a random n-lift, taking G to be any of these 6 regular graphs or any other 6 regular graph that you can think of, then you get a different model, a different distribution for 6 regular graphs. So like a first question would be, are these distributions similar or different? And the answer is, well, the answer is going to be no, but let me move something out of the way. So if you take the base graph to be the bouquet with d over 2 half loops, a random lift that you obtain, or the distribution of random lifts obtained, is contiguous to the uniform model of random 6 regular graphs or d regular graphs. And by contiguous, I mean the following. So if you have two models of random graphs indexed by some parameter n, they're contiguous if whenever you have a sequence of events everything is indexed by n, so maybe I should have an n everywhere in the first model. And whenever this probability goes to 0 as n goes to infinity, so you have any sequence of events that is rare, the limiting probability is 0. So this happens even only in one model, even only if it happens in the other model. And also you can replace this 0 by a 1. So typical events or atypical events are the same in the two models. But you could have other events whose limiting probability tends to a constant in both models, and these constants are different. For instance, you could have, the probability of having no triangles, well, like is Poisson in the limit in both models, but maybe the expectation is different. So it turns out that for the bouquet of d over 2 half loops, the random lift model that you get is contiguous with the uniform model of random graphs that comes from the configuration model. So you just pick, you have a bag with all d regular graphs on n vertices, and you pick one at random. However, this is not true, for instance, if you pick this as your base graph. It's very easy. You can show that by showing that if you pick a uniform d-regular graph with probability tending to 0, it's going to be a lift of this. And in fact, in general, if you pick two different 6 regular or d-regular base graphs, the random lift that you obtain from each one is not contiguous. So you have an infinite collection of different interesting distributions for the irregular graphs. So you can think of these as a generalization, a non-trivial generalization of the uniform model of random graphs that has been studied using the configuration model of Bolowash. Any questions about the model? Okay, so let's talk about. Yeah, go ahead.
Sorry. So the question is it true that this interest to consider these random n-lift models came exactly from this, that when you consider a bouquet, you get that it is so very close to the deregular case, and the question was, is it true for if you consider for other graphs or not?
I don't think that was the origin of people looking, like, because I think that's fairly easy to, I think an easy first moment argument shows that a random deregular graph is not a lift of K7 or of this. Well, this is very easy because if it was a lift of K66, it would be bipartite, because the random lift has like, well, like lower chromatic number, and this has chromatic number 2, and it's well known that the regular graphs are not bipartite unless the unless these 2, I guess. Yeah, for d equals 3 they're not already. You'll have odd cycles. So that's not the motivate. Well, I think that the physicists had looked at that already, or also even people in coding theory, because, well, not exactly in this exact context, but they have looked at similar things, because there are some situations in which you have a certain graph, but having short cycles is bad for some reason. And if you take a lift of this graph, typically, well, you could have also like copies that are components of this graph, but with high probability, you increase the girth. So there are some graphs like Tanner graphs that are used in coding theory that have some good properties, but then having short cycles is bad. And then if you take a lift, not random, but just as a deterministic lift of this graph, these improve some of the properties that they need in coding theory. And in statistical physics, there are also some situations that taking a lift is good because also, yeah, you increase the girth of a certain graph. So, of course, sometimes these lifts are not random, but I think that this motivated the study of random lifts, maybe under different names and from different points of view in some other fields. But I'm not sure if there are other reasons or motivations. Since I like the configuration model, I just thought that this was a nice generalization.
Okay, thanks.
So in a paper by Amit Linyal and Matuszek, of a series of papers involving Amit Linyal and sometimes other people, they look at things like the chromatic number or the independence number and other related parameters for random lifts. And well, they prove many things, and maybe I should have stated them, but they give they give the following upper bound. Well, so they look at the chromatic number of a random lift of a fixed graph. So you fix a graph, you take a random lift L, and they show that the chromatic number is with high probability, or AAS. Well, let me define AAS. So AAS, asymptotically, almost surely, or with high probability, we say that the sequence of events happens AAS if the probability tends to 1 as n goes to infinity. So they show that AAS, the chromatic number of a random lift, is at most delta over log delta time. Well, there's some hidden constant here, where delta is the maximum degree of the base graph or the lift. And then they also look for lower bounds, and they show two different lower bounds. They first show, so they want to relate the chromatic number of a random lift to the chromatic number of the base graph. And they would like to prove this with some constant here, but they're able to prove that with a square root. And they also to prove another lower bound using the fractional chromatic number. But they have a log square.
Why do you want to use fractional?
Because it leads to a beautiful proof. It's a short but beautiful proof. In some sense, it seems, I think, I don't have an intuitive, clear way to say that, but it seems that the fractional chromatic number of the base graph seems to reflect better the chromatic number of the lift. I think I don't think I can say anything smart because I haven't looked at the proof for a while. Yeah, no, I cannot say anything smart why they pick the fractional chromatic number, but it's a short and beautiful proof, and when you look at the proof, you say, okay, that makes a lot of sense. But I haven't looked at that for a while, so I cannot say anything clever. But they believe that.
Sorry. And is a upper bound?
Yeah, so
for chromatic number of list, delta of over log delta for fractional, yes?
Sorry?
I mean, there are upper bound for just chromatic number, or not fractional chromatic number of graph is not bigger than delta over log delta. It is Bernstein result.
Yeah,
and the question is the same upper bound for chromatic number of lift.
Oh, in terms of that, of the fractional chromatic number? Okay.
Yes, but the upper bound.
They
So
don't
the
provide.
question is about the fractional chromatic number of lift.
Yes,
right?
so they don't give that in their paper. So, and I don't know. I think yeah, like the fractional chromatic numbers seem to be tailored for the lower bound, at least in their proof. They don't give anything else. That's the only place they use the fractional chromatic number. So yeah, so if you're asking for a function of f of g, this is open. So in fact, I should have mentioned that this paper has lots of open problems. And so it's a paper that's full of clever ideas, but they don't seem to be wanting to optimize or like squeeze the last drop of their ideas. So there are many open problems mentioned in that paper. So I'm sure that it'd be interesting to find an upper bound here in terms of the fractional chromatic number. So I just don't know how to do it. In fact, I've been thinking about, sorry, my slide looks a bit messy now. I think that in many situations, not in all situations, but there are many situations that I think that this is going to be the true answer without fractional. But that's certainly not in all cases, and I don't know if you can find more general bounds in terms of the fractional chromatic number. So yeah, my slide looks a bit messy now, and all of this is going to disappear in a second. So that's an open problem that kind of motivated me. And in fact, if you take G to be the complete graph on d+1 vertices, so the complete graph that's d-regular, in fact, for that case, you get, well, this is true. And if I go to the previous messy slide, the upper bound and the lower bound coincide because the chromatic number and, well, and the degree just differ by 1 for the complete graph. So for the complete graph, you have that asymptotically almost surely the random lift, the chromatic number of the random lift is, oh, that's a log. Or I can put I can just put a D. And here maybe this theta, it's not a very good notation because what I mean, because these are constant, these fixed. So what I mean is that I can bound this between, well, I can place here a constant C and get an upper bound, and place a constant C prime and get a lower bound. That's what I mean by this theta. Because these
What constant do you expect?
Oh, in fact, that's what we do in this work. So yeah, so at least for G being the complete graph, we determine this, and so in fact we get a 2-point concentration. So yeah, so I'll say that in shortly in my next slide. So anyways, so if you don't care about the constant, in their paper, they show that this is the answer for the random lift of a complete graph. But then they would actually like to determine what this chromatic number is, and in some, because they conjecture, and maybe I'll show the conjecture now, that is, if you fix a graph G, take a random lift on n vertices, then as n goes to infinity, the chromatic number is going to be concentrated on one single value. So if you fix a graph G, there's a constant k sub g, such that almost all, all but a vanishing fraction of random lifts have chromatic number kg. So
the conjecture is not only for regular graphs, right? It is
no, the conjecture is for any graph G, and it's a wide open conjecture. I think it's very hard. So in some sense, we're trying to determine. So in this paper, we try to determine this for G being the complete graph, or for, in some cases, for the irregular graphs. So if you take G to be the complete graph, well, it's very easy to see what the chromatic number is for a random lift of K, well, of K2 and K3. Oh, sorry, K3 and K4. But the first case where this is not known is K5, which would be, we would be talking about 4 regular graphs. The random lifts have chromatic number either 3 or 4, and it's not known which one it is. This would be very similar to determining the chromatic number of 4 regular graphs, which is known to be 3, and it was proved. It was proved by Achlioptes and Moore using, well, the analysis of some greedy algorithm using differential equation method. So it's kind of a tricky thing, and I assume that the same method should work here to prove that the random lift of K5 has chromatic number 3. So using Wormald's differential equation method to analyze some greedy coloring algorithm. So what we did, so we did nothing for K5. Well, but for we fixed the D. Well, or we were not able to get rid of these 4 for K5, but we looked at the problem for the random lift of a general KD plus 1, where D is fixed. And we determined, so we found a specific K, which is defined to be the smallest K such that this inequality holds. And roughly, for large D, this K is roughly 1/2 of D over log D. So this is the constant that you were asking me before, Rita. So, but we fixed an exact, we found an exact K such that asymptotically almost surely, the chromatic number of a random lift of KD plus 1 is one of these 2 values. And for roughly half of the integers D, we in fact get rid of this value and we find a 1-point concentration. What I mean by roughly half, I mean that there are some intervals which are kind of, growing, but, and then, I don't know, if your D falls into one of these intervals, you're in this situation. If D falls into this other interval, you're in this situation. And these intervals kind of grow, but like very slowly, but the ratio between 2 consecutive intervals tends to 1. So roughly half of the integers fall into this category. So this is for the random lift of a complete graph, but the upper bound, so showing that these many colors or these many colors are enough, in fact, works for any D-regular graph. But of course, this upper bound is tight in the case of, well, I'll say something about that in a second. So if instead of taking a random lift of the complete graph, you took a random lift of the bouquet with D over 2 loops, let's assume D is even for simplicity, then what we would be talking about, this random lift would be just the regular model of deregular graphs. So what we would be recovering is some analogous results that we proved for uniform deregular graphs with Graham Kemkes and Nip Wormel some time ago, which were improved by Amin Koya-Oglan and two of his co-authors. So this same result verbatim holds if here, instead of L, you put a random deregular graph, which you can think as a random lift of the bouquet. So in some sense, what we knew for the random lift of the bouquet, we've extended to the random lift of the complete graph. And in fact, the upper bound holds for the random lift of any deregular graph. However, the lower bound could be very far off for in some cases, like because in this case, since this is bipartite, the random lift is also bipartite, so this upper bound is kind of far off. But in this case, it's tight, and in this case, it's tight. And what I would like to know, and I thought about that for a while, well, it's been over a year, so, and I didn't get very far, but I would like to extend the class of of regular graphs for which this result is valid. So you need them to be very regular in some sense. But I'm sure that there's a larger class of deregular graphs for which for which this is valid, not just the upper bound, but the lower bound. So that's one thing. And also maybe not with this, not with this number, because this is not the true story for this graph, but I would like to maybe solve Amit Linyala and Matuszek's conjecture for at least for G being a regular graph. And maybe less ambitious, and if G is regular graph, I would like to prove that and maybe determine what this number is. But this seems hard, and I really don't know how to do it. Okay, any question about our result? Okay, so I have the feeling I've talked a lot. I think I might run out of time. So how much time do I have just to get an idea?
So usually it's 1 hour and a half in total. So you may finish at 8.5.
Okay, then it's going to take less than that, but then I can. Okay, so
less and bigger is also fine, as you wish.
Yeah, no, I'll certainly use less than that, but yeah, like it's good to know that there's some slack. So as I probably said in other times that I delivered this talk, I put up this slide just to impress people, but if I wanted to be very modest, I would say that the main tools are a first and second moment method, only that complicated ones. But in fact, yeah, like this first and second moment method take a lot of work, and usually for this kind of problems, the main bottleneck is that you have to do very hard optimization, non-convex optimization, like optimization of some non-convex functions, which is typically hard, and it doesn't always work. So sometimes things don't maximize where you would like to. Then you need to, well, compute like estimate the asymptotics of some complicated summations, and there are different methods to do that. We use both, some Laplace summation tricks and some saddle point method tricks that involve like computing integrals on some appropriate contours on the complex plane. Those things are technical, but they always work. This thing sometimes doesn't work. So sometimes for these kind of problems, this is the main bottleneck. These two other things are just a lot of work, but they often work well. And we also had to use some algebraic graph theory, which was fun because I learned some things that I didn't know. Okay.
I'm sorry.
Yeah.
Your work based not on Ecliptus and null, but on algebraic graph theory. Yes.
Well, we have to use a bit of all. We have to use all of these things. We have to extend some inequality that Ecliptus and Moore used, and we have to use also some algebraic graph theory. So we use all these things, and I'll say a little bit about each one of them without getting into the gory details. So all I wanted to say is that all of these things are technical, but the one that sometimes fails and then you have to give up is this one. Because when this fails, that means that our method does not work. And that's what happens. In fact, if you try to take the random lift of K5, our method doesn't work because some functions that you're trying to maximize do not maximize at the place that you want. So the variance is too big. So the method fails. And then that's why for this, if you're taking the lift of K5, the approach that I suggest, which I was lazy about working on, was analyzing a greedy coloring algorithm using differential equations. So anyway, I'll talk a little bit about some of these ingredients. The first thing, and the most basic structure of the paper, is that for the lower bounds on the chromatic number, we just use a first moment argument. So we denote the number of, we fix a k, we have a target k that's lower than the number of colors that we want. And we want to show that the chromatic number is less than that k. Sorry, no, is great. What am I saying? We want to show that the chromatic number is greater than some k. So k colors are not enough. So we create a random variable that counts k colorings of the random lift. We compute its expectation and show that for k less than kd, which is our target value, this expectation goes to 0. So an easy first moment method, so Markov's, an easy application of Markov's inequality shows that the probability of having such a coloring goes to 0. So the chromatic number has to be bigger with high probability. So that's very easy, only that computing this expectation is not easy at all. So for the upper bound on the chromatic number, we want to show that for a different k colors are enough. So you pick a k that's larger than kd. And now, instead of looking at the number of k colorings, we hurt ourselves a little bit by restricting our attention to what we call strongly equitable. So we want to color our random lifts by keeping each of the fibers equitable, meaning that each color appears the same number of times in each fiber. So we restrict the set of valid proper colorings, just because these add symmetry to the calculations and makes things life easier, but also because we think that at least for base graphs that are highly symmetric, those colorings are the ones that play the main role. So if y counts those colorings, we compute the second moment of the number of such colorings. And if we have enough colors, we show that this second moment is at least, well, it's of the order of the square of the first moment.
I'm sorry.
Yeah.
How does your stochastic matrices looks? Look.
Oh, they will appear soon. So in fact, well, in fact, I can tell you now, but if you count, well, they'll appear. Okay, no, I'll tell you in the next slide about the stochastic matrices. But in any case, when you have enough colors, the second moment of the number of strongly equitable colorings is around the square of the first moment, and then you can apply Paley-Zygmunt inequality, which is essentially it's similar to Chebyshev's. It's stronger in our setting, so you can think of this as a variation of applying Chebyshev inequality, but basically the probability of having a proper coloring of this type is at least this ratio. And if this ratio, well, we show that it tends to a constant that's non-zero. So we show that the probability of having some K coloring is at least some non-zero constant. But that doesn't show that you can color with K colors with probability going to 1, but with probability bounded away from 0. But unfortunately, this constant is strictly less than 1. So we would like to boost that to a 1, but that's not possible. Well, like this thing is not 1 because of the influence of short cycles in the random lift. So short cycles kind of artificially inflate this second moment by a constant. So so you get something that's less than 1. And we'll talk about that, how to fix that later on. So I'm going to talk about stochastic matrices very soon. So, but the long story short, our paper basically consists on proving these two theorems by, so basically computing these three moments. The first moment of the number of colorings, the first moment and the second moment of the number of strongly equitable colorings. So all we need to do is compute these moments, which is tricky, but then once you have them, a first and second moment argument gives you what you want. So how do you compute these moments? So suppose we want to compute the expectation of the number of K colorings, and the other ones are done in a similar way. So you can compute this expectation by summing overall, let's say, so our model, we're building a random lift, so you could sum overall lifts. Which way should I do that? Well, maybe I'll just do it like this. You can just count. Yeah, so you can just sum, but maybe I'll just do it like I was going to do. You can just sum for all lifts the number of colorings of this lift times the probability of getting such a lift. But basically, you can turn that into a counting problem. So you can count pairs of lift and proper coloring of that lift and divide by the number of lifts. Since it's a uniform probability space, the expected number of colorings is just the number of pairs, lift coloring, where C is a proper coloring of the lift, divided by the number of lifts. But to compute this numerator, it's very hard to fix a lift and count how many colorings you have. It's a lot easier to fix a coloring and count how many lifts are compatible with that coloring. So that's what we're going to do in some sense. Like, it all amounts to a counting problem, counting this numerator here. Like, the denominator is easier to count using some sort of configuration argument. So basically, fix the coloring, all the colorings, well, yeah, fix the coloring and then count how many lifts you can build for which the color is proper. So to do that, we're gonna fix a certain number, some parameters, do this count for those parameters, and then sum over the range of possible values for these parameters. So let's see how we do this. And I'll try to not to give a lot of detail, but at least give the idea how this is done. So for each fiber, I'm going to decide how many vertices will be colored with each of the colors. And this is going to give me some parameters, the A's, that tell me, in fact, I divide by n. So the A's give me the proportion of vertices in this fiber of each of the colors. And I do that, so I have a set of 8 parameters for each of the fiber. For this fiber, they're different. You can see the proportions are different. Then for any 2 fibers that are adjacent, I count how many edges, let's say, go from yellow to blue. And how many go from yellow to red, how many go from yellow to green, etc. Which should be the same. So the number of edges going from yellow to blue should be the same as the number of edges going from blue to yellow from the other side. And then those are the proportions, so I divide by n. So these B's tell me the proportions of edges going from yellow to blue or from yellow to red, etc. So I'm going to fix the values of these A's and these B's, and that will correspond to one of these terms in this sum. So once I fix these A's and these B's for every fiber and for every pair of fibers, I want to count the number of lifts that are compatible with a coloring that has those parameters. So yeah, maybe before I proceed, since Rita asked about the stochastic matrices, well, you can think as the A's here as a probability distribution because there are proportions that add to 1. So for each fiber, I have a probability distribution that I can put in a matrix, and I have d+1 fibers. If G is, let's assume that G is KD+1. Otherwise, well, it's just the number of vertices of the base graph. And each row corresponds to a fiber, and it's a probability distribution on the K colors. So this is a D+1 by K matrix where the rows are probability distributions. So this is a stochastic matrix that encodes. So for each fiber, I have a stochastic matrix encoding the proportion of colors in that fiber. So that's going to be, well, so once I fix those parameters, I'm going to count the contribution to the expectation from colors satisfying those parameters. So the A's and the B's, well, were integers divided by n because they counted vertices or edges, but I normalized by n. So they live in this lattice. That's going to be important later. These parameters live in some lattice. Also, they satisfy some equality and inequality constraints. So the A's are, of course, between 0 and 1, so are the B's. And in fact, the A's are a probability distribution for each of the fibers, the A's add to 1. And for each pair of fibers, well, I have these constraints. All of these B's that count edges going from yellow to something add to the number or to the proportion of yellow vertices here. And all of the edges that go, I don't know. Well, so you have certain sums of B's must be equal to certain A in here, and certain sums of b's must be equal to some a there. So I'm really saying more than I planned. So all I want to say is that once you decide, well, you want to decide what the a's and the b's are. There are some easy equality and inequality constraints that they satisfy. So long story short, the a's and the b's live in some lattice, also live in some polytope that's given by the inequality constraints. And also this is intersected with an affine space given by the equality constraints. So these parameters live in the intersection of a polytope, a lattice, and an affine space. And this will become important. Not so much what these equations look like, so you can forget about the equations, but just remember these three things. And as I said before, for each fiber, these A's live in a stochastic matrix because, yeah, well, D plus 1 by K, because the rows are probability distributions. So I would like you to believe that once I specify a set of A's and B's satisfying these constraints, basically I can compute the contribution to the expectation from colorings of that with those parameters. Like I can say, okay, how many colors do I have satisfying these parameters? I have to decide which vertices in each fiber get each color, but I have the quantities decided. And then I have to count how many lifts I can build satisfying these colors. So I just have to count ways of sending the right, you know how many edges go from yellow to blue, so you just have to permute them. So this is going to be a bunch of multinomials and factorials and things like that. But once you know the parameters, it's just an exercise for a graduate student or for an undergraduate student in Russia, probably. For a high school student in Russia. Okay, so I was going to say, yeah. Yeah, so then that allows us to write the expectation as a closed formula. But we would like to find for which for which set of parameters A and B, this give them the main contribution to this expectation. So this is an optimization problem. Like this is a very complicated expression, a very complicated sum. So we would like to see for which values of A and B, give me the main contribution to this expectation. And we claim that this contribution comes when all the A's and all the B's are the same. And this, to prove that, so this is an optimization problem in which we had to extend a result by Ackley-Optas-Naor, in which they do something similar, but their parameters live in a doubly stochastic matrix K by K. Well, in our case, our matrix, their matrix is doubly stochastic, but they relax that. So they look at stochastic matrices, which are square, K by K, while our matrices are rectangular. The fun fact as well is that their optimization problem arises when they're computing a second moment. So their K by K matrices, in some sense, arise when looking at pairs of colors. And so they're kind of counting, well, in their graph, they're kind of keeping track of how many vertices are colored of certain color for coloring 1 and certain color for coloring 2. So their optimization arises from their second moment, calculations, but in our case, because we're looking at lifts, the first moment already involves this complicated optimization, which is very similar to a second moment calculation of Ecliptus and more, but it's a first moment calculation. So that was surprising. Our first moment calculation was harder than Ecliptus' second moment calculation. However, our second moment calculation was not as hard. So that was a bit surprising.
Because this condition of having only strongly equitable colors.
Yeah, so restricting our attention to strongly equitable colors simplifies things, but then there's a bit of luck. It's still a much more complicated, so maybe I'll clean that a little bit. So you do something similar when you're computing for the second moment of strongly equitable colors, but then for each bin, you need to keep track also. You have like a doubly stochastic matrix for each bin that tells you how many vertices are of one color and how many vertices are in the other, but now both rows and columns add to the same, to 1 over k, or well, you can normalize things whichever way you want, so maybe to 1. So it's still a lot more complicated because now you have many, many doubly stochastic matrices, but then there's an easy trick, well, not so easy, but like easier than we thought, that allows to reduce our second moment calculation to Ecliptus and Naors. So even though our second moment is not that easy, but there's an easy trick that allows us to reduce it to this. However, for the first moment, it looks like a generalization of their approach. So that the optimization took us a lot more work, which, yeah, but this is because using general colorings versus strongly equitable ones. Okay. Yeah, so I think we maybe lost audience along the way. Is it just you?
Yeah, we have lost several people, right?
Yeah.
When I have started speaking about the proofs.
Okay, well, I'm happy. Like, well, I'm happy to keep going, but like, if I'm talking too much and it's only you, like, you can stop me.
No, I don't think so. Yeah, it is fine for everyone
Okay.
who's here, I think.
Okay. So, but long story short, maybe what I said sounded complicated, but the summary is that we can compute these moments and give some very ugly but exact expression, which looks as an ugly sum of something here that contains multinomials and factorials, which is like huge. It's like it fits more than one line, but there's nothing deep about it. But the parameters live in the intersection of a lattice, a polytop, and an affine space, and that's all that matters to me now. So yeah, so for each of the moments, our sums, as I said, look like this, where we're summing over some x's that live in the intersection of a polytop, multidimensional polytop, lattice, and affine space. So, of course, we would like to have a simple asymptotic expression for this sum. The first thing we can do is get rid of all the multinomials and factorials using Stirling formula for approximating the factorial, and we turn the terms into something that looks like this: some exponential part and some polynomial part. But the exponential part contains an n here, and this is a function that does not contain any n's. So this is a function of x, where x lives in this domain here. And then this is a polynomial in n, which also depends on on x. So once you have this approximation for each of the terms, if you only wanted a crude bound on the moment, so if you just cared about the exponential behavior, you could do the following. First, look at this function here. So this is a function like so now we're doing calculus. So you can think of this as a function defined on a polytope, and you suppose that you're able to optimize. This function is not convex and not nice, but suppose that you can optimize this function and show, well, maybe forget about the lattice for a second. This is a polytope intersected with an affine space, which gives you a smaller polytope living in R. So this is a polytope in RD, but it has lower dimension because you slice it with an affine space. So if you can optimize this function and show that it maximizes somewhere, and this maximum is unique, so it has a unique global maximum, then you're happy because the term corresponding to x naught gives you the exponential contribution, because since there are only polynomially many terms, and this comes from the fact that this lattice here only has polynomially many terms in this, it's a power of n in the polytope. There are polynomially many terms, and each of the terms is exponentially dominated by the term where this thing in the exponent maximizes. Then you get this upper bound here. This is a Moissan polynomial times e to the n times f at x naught. But also, this term here, well, the x naught term is also a lower bound. So you basically get that m is some polynomial times this exponential thing. So if you only care about the exponential behavior of the moment and you don't care about what this polynomial factor looks like, you're done. However, this optimization problem, as I said, is hard, and we had to generalize some work that Akliopoulos and Naor did. But then if you want to really obtain an asymptotic expansion for these polynomial factors, there are different things that you can do. But the end of the story is that always when you have a sum like that, if you find a term that dominates exponentially and you have only polynomially many terms, you can approximate the sum by the term that gives the maximum exponential contribution times something else. And it's some constant times n to the r over 2 times that term, where r is the dimension of the affine space that we're slicing the polytope with. So remember, this is a polytope in Rn, and we slice it by an affine space given by this linear system of equations. And if the dimension of the kernel of this matrix is R, that means that my summation domain really lives in an R-dimensional place. Well, so basically this R appears here. So you get the square root of n to the power of R. If you want an easy toy situation where this happens, so if you were summing the binomial coefficients and you forgot, I guess, like you missed that day in school where they teach you that this is 2 to the n, so we forget about this. You could approximate asymptotically this by the largest term, the term that gives you the highest exponential behavior. But then what we are missing here is really some constant times the square root of n. If you do the asymptotics for this, basically that tells you that this term is not enough to give you the whole weight of this sum, but it's enough to sum around a small window around this term. So in some sense, what I'm saying is that if you're trying to estimate this sum, the term that gives you the highest exponential contribution is not enough, but it's enough to sum around a vicinity of that, of radius something like square root of n. So you have roughly these many points. I'm raising to the power of r, where r is the dimension of my polytope. Here, the dimension is 1. You can think of this like, this would look like a situation where my polytope is just, yeah, like an interval in the real line, and here you have to do some rescaling, but basically, yeah, that's where this square root of n comes from. So what we're doing, well,
so
anyways,
just
sorry?
a short question. So is there some maybe general result from probability theory that tells you if you have some random vectors and you know that the dimension, you might apply something like central limit theorem and get the same or not?
Yeah, it's very related to the central limit. So here, if you normalize this, you can think of this as a probability distribution, like a binomial n1/2. And
yeah, I understand. And here, in your case, it looks like you have some
so it's
space and some vectors, and just you look on dimension and do
yeah.
this.
So if you normalize these terms and you interpret them as a probability distribution on the points in this polytope, however, it's a strange probability distribution. Remember that each term corresponds to fixing some parameters for what you want your colorings to look like, and then so you're picking maybe a random coloring weighted with a probability that depends on how many lifts are compatible with that coloring, and then some sort of central limit tells you that so this would be the place where you expect to land, and then there's some standard deviation, and yeah. So morally speaking, this is true, but I don't know if any probability tool would spare you from doing the nasty calculations. It's just looking at that with different glasses, but I think the calculations behind would be the same. But yeah, that's a great comment, because like it brings more intuition to what we're actually doing. In other words, if you wanted to apply some kind of multidimensional central limit theorem here, the calculations that you would need to compute the standard deviation probably would be equivalent to what we're doing. So yeah, I don't think it would give any shortcut. But anyway, so that's the moral story of what's going on. So we know then what this is once we know what the dimension of our summation index space is, but we want to estimate what this constant is. And this computing this constant is technical and complicated, but it's not, but it always works. And I've done similar calculations in other papers using either some Laplace summation tricks or some complex saddle-pond integration tricks. And in this paper, we use both because we had to do something like that 3 times. And in some cases, it seemed to be easier to use one method or the other. For this one, you have to basically express this as some generating function and then use saddle point techniques to estimate the asymptotics of the coefficients. But this generating function arises naturally in some of the cases, but in some others, like we couldn't find an easy way, so we used a different technique. So I'm not going to talk at all about the saddle point method. I'll say something about this. So we use a method inspired by what they do in a paper by Greenhill, Jansson, and Rucinski. So to compute that constant, you have to understand what this lattice looks like. So, well, you have to understand what the Hessian of this function is once you restrict it to the affine. So the restricted Hessian to the affine space, which is an easy calculation. But you also need to know what the volume of the fundamental cell of this lattice is. This lattice was originally a very boring lattice where the fundamental cell has volume like, well, 1 over n to the d. However, we are slicing this by an affine space. So then in the resulting polytope, the lattice now looks lopsided. Like, so cells are not these nice cubes, but the fundamental cells look complicated. So anyways, if you can compute, and that involves like some algebra that comes from understanding what the domain of summation is. So this was complicated in the paper. So in a paper by Greenhill, Jansson, and Rucinski, they're doing different things, but they have similar calculations, and they start looking at the lattice that they get. And what we realized is that you can reformulate some of they give like a theorem that you can apply as a black box to compute this C using information about this lattice. But we were able to reformulate that by forgetting about lattices and counting spanning trees or maximal forests in some graph. And this graph has nothing to do with our base graph or our random lift. This graph has to do with the graph that has this B as its incidence matrix. So remember this B, and I'm going to travel back in time, basically came from the constraints, is the matrix of the linear constraints of the parameters that we're summing over. But this graph, these equations have ones and zeros as coefficients. So the matrix of this system of constraints has only zeros and ones. So we look at that as the incidence matrix of some graph. And it turns out that counting spanning trees in this graph, well, it's or spanning forests, because it's not connected. The number of spanning forests in these graphs turns out to be the same or essentially strongly related to the volume of the cell in this, the fundamental cell in this lattice. So we ended up having to count spanning trees or spanning forests using the matrix tree theorem on some graph whose incidence matrix was given by some constraints. These constraints depend, of course, on the base graph. So you need to understand, you need to know something about the spectral properties of the base graph to understand what the spectral properties of these auxiliary graph look like. But that was interesting, and I think it was easier than using the method by Greenhill, Jansson, and Rucinski. So I think it's a nice tool, well, for future moment computations of similar nature. So I think that was, I don't know. Okay, so I'm running, like now I think I'm running out of time. So I don't know how much I'll just try to say very little about the next two slides, and that's pretty much it. So the first thing is that the probability of having strongly equitable colorings is at least the ratio between the square of the first moment and the second moment. And these, doing all these complicated things, we compute the moments, and this magically ends up being a constant, but it's less than 1. And the reason is that this variance here is affected by the number of short cycles. So what we do, and I'm going, I think I'm going to ignore all this. But the long story short, what happens is that if this is my probability space and I slice it according to how many cycles I have of different lengths, so each of these slices corresponds to conditioning saying, okay, I have Zi is the number of cycles of length I. So when I take a random lift, suppose that I condition on having 7 triangles, no 4 cycles, 2 cycles of length 5, up to maybe, I don't know, 17 cycles of length 100. If I condition on those things, and I look at this slice of the probability space, in this conditional probability space, it turns out that the probability of having a proper cake coloring is asymptotic to a different constant, but it's closer to 1 than C. And we can make it closer to 1 by making 100 large. So if you specify the short cycle counts up to length as 100 or 1,000 or 1,000,000, and you condition on having exactly a certain number of triangles, 4 cycles, etc., then in this conditional space, you can make this ratio as close to 1 as you want by conditioning to longer and longer cycles. And this is what Wormel's first moment, a small subgraph conditioning, Wormel and Robinson's small subgraph conditioning method does, which was, kind of also generalized by Janssen.
And then you just summing up over these conditions, right? So whatever conditions you consider, you will always have density which is closer to 1.
Yeah, but you don't do it in this way. You apply this fancy result as a black box. So that's the idea behind, but you don't do that like this. What you do is you compute some factorial moments, basically. Like you do some calculations. So you compute things that look like this. So these are joint falling factorial moments weighted by the number of coloring. So you do compute these strange moments and basically show that in a probability space weighted by the number of colorings, the cycle counts are Poisson. So in the unweighted probability space, the cycle counts are Poisson. But if you weight your probability space by Y, which is the number of colorings, the cycle counts, the number of triangles, let's say, or the number of cycles of length 100, is still Poisson, but of a different parameter. So you compute what these parameters are. You compute then what this series is, and if magically this constant that you get magically is the same as the ratio between these two moments, then you conclude what you want. So you forget about all this intuition that I said, and basically you just have to compute the asymptotic law of the number of cycles of a given length in some weighted probability space, compute some numbers, and then this is magic. If this series coincides with the ratio of the moments, you're done. But this is highly non-trivial, like the proof of this result. But the idea, like a simplified intuition of the idea, is what I said. But then you forget about the intuition and just try to compute these moments here, and hope for the best, and hope that by magic you get this ratio. I think even Nick Wormel, who was one of the inventors of the method, kind of says that, yeah, this works by magic, like, or at least the first times he applied the method, he thought it was kind of a miracle that you get that number. Probably he's got a deeper intuition about that than I do. And the last thing I want to say, and I'll say very little, but some of these calculations involve understanding the number of cycles of a given length in your random lift. So for instance, the number of cycles of length 1, 2, 3, 4, 5, 6. And essentially, to do these calculations, a crucial point is to be able to count in your random lift how many cycles of a given length you have. And to do these calculations, you can translate that into investigating close non-backtracking walks. So a non-backtracking walk is like a closed walk that's non-backtracking is a closed walk that goes follows the fibers of, well, I'm taking the walk maybe on the base graph. Yeah, so sorry. So if I want to count cycles in the lift, I can study close non-backtracking walks on the base graph. And non-backtracking means that I cannot do a sharp U-turn like this, because taking a sharp U-turn on the base graph would mean that I have to return through the same edge on the matching on my lift, so I cannot do that. So yeah, so I just want to say that there's a close connection between cycles in my lift and non-backtracking close walks in the base graph, and that something that's crucial to understand what these cycle counts are is to be able to count in my base graph how many closed non-backtracking walks I have of different lengths. And this can be done using some algebraic tools that relate this non-backtracking walk to a simple random walk on the base graph. So if you know the eigenvalues and some spectral properties of your base graph, you can infer some information about the number of those non-backtracking walks. And there are some very nice algebraic tools that I won't have time to talk about, but there are several papers by Friedman that introduce all this machinery. And yeah, I'll stop here because I think I've grossly run out of time. Just to finish, I'll just, that's a repetition of an older slide. I just wanted to mention that this paper by Amit Linial and Matuszek has many very exciting open problems and many cool ideas, even though they're not trying to squeeze the last drop of power of their ideas. They're just, I think it's like a starting point rather than a finishing line, that paper. Okay, well, thanks for your attention. I know it's late in Moscow.
Thank you very much, Xavier. Are there any questions?
I have a couple questions, if you could. The last bunch of slides, this is essentially just to get a lower bound on the expectation. Is that right? Like a lot of the work where you're restricting to certain terms. That's,
So which slide?
oh, I don't know, somewhere around 9 or so, or
Well, so there are different things. So we need to compute different moments.
right.
And these moments, like the derivation of an exact formula for these moments follows a similar approach. And in the end, everything that I was mentioning here was just to obtain the asymptotics for the moments. They're expressed as some gross sums.
Right.
And you want to find the term that gives you the main exponential contribution, and then just show that you can restrict to a few terms around that term, and they give you the whole sum. The second thing I said, or the next thing I said, is that once you have computed those moments, the lower bound of the chromatic number comes from showing that the expected number of colorings goes to 0 if you don't allow enough colors. So that's for the lower bound on the chromatic number. For the upper bound, no, I'm saying it the wrong, no, I'm saying it the right way for the lower bound. For the upper bound, you restrict your attention, you hurt yourself and restrict your attention to strongly equitable colors, but you still need to compute the first moment and the second moment. And the techniques for computing the moments are similar in all three cases, only that, yeah, that things get more complicated for a second moment, but they get simpler because strongly equitable simplifies the calculation. So, but in any case, the computations of the moments are similar. But here, what I was saying is that this ratio does not go to 1, but we could make it go to 1 if we condition to knowing how many triangles, like imposing a number of triangles, a number of 4 cycles, a number of 5 cycles, etc. And the way of doing this kind of seeing how fixing the number of cycles of short length allows us to bootstrap this bound and get something that's close to 1. The way to do it is just applying this small subgraph conditioning method as a black box, which requires you to compute some moments that involve, I'm just writing something slightly simpler than, yeah, it involves computing, well, things that are more complicated than this, but in particular, you need to compute things like this. The expectation of the number of triangles times the number of colors. And to do this computation, you need to understand how many triangles there are in your random lift. And to understand that, you need to understand the non-backtracking walks in the base graph.
Okay. No, that's
I don't know. Since I didn't understand your question, I just...
No. I was... Okay, that's fine. And can you go back to page 7?
Mm-hmm.
So you had mentioned that for some cases, right, you didn't have, okay, let's go back one more. Let's go back to 6. Oh, yeah, stop right here. So you said for half of the values of D,
Mm-hmm.
right, you have your value. For the other half, you said these techniques didn't really work. Do you still get like a range of values? Or
Yeah, you get these two values.
Sorry?
You get, so for instance, I'm making it up. So but for instance, if G is K 100, right, maybe the chromatic number of the random lift, maybe you know it, and right, it's, I don't know, 7, but if you replace that by 101, maybe you know it's either 7 or 8, but you don't know which one.
Right. Yeah. sorry, when I was sort of writing down my notes, I had thought maybe you didn't even have a range of values for half of the Ds.
Yeah,
but
no, you always have these
the
two
third
values.
line, those two values work all the time.
Sorry?
The
Yeah.
third line says those two values work all the time.
Yeah, they work all the time. And in fact, my suspicion, maybe I should say something more about that. Is that this is the truth that
Okay,
probably, but in order to do that, Koya Oglan, what he did for the uniform model, which would correspond to a bouquet of D over 2 loops, he used some ideas that come from statistical physics to say that if D is large enough, still a constant, but larger than some very large constant, you can get rid of this value. But what they do is they use some ideas that come from, there's some non-rigorous ideas coming from statistical physics. Their paper is rigorous, but is inspired by some non-rigorous papers that tell you, if you look at the space of color assignments that might not be proper, but you look at the geometry of color assignments, and there's some very complicated geometry there, and they do. So what they do is some second moment method, but instead of counting colors, they count clusters of colors in this very strange geometry using some intuition that comes from statistical physics. So all what we did about counting colors is done for clusters of colors that are, so basically you can think of those are some space of colorings that are proper, and you can go from a coloring to another one if you can just flip the color of a small number of vertices. So there are some clusters there. Some are big, some are small, and understanding how big these clusters are and how far apart they are allows them to do a fancier second moment calculation and get rid of the second value for large D. But they do that for the uniform model of the regular graphs. And I'm pretty sure that the same can be done here, but it's very complicated, and maybe I'll let Koya Oglan and his team do that. And no one knows what happens for small d. Like you can probably do that, like for d larger than 1 million, but for d equals 5, their methods don't work.
Okay, thank you.
Yeah, you're welcome.
Okay.
Yeah, so thanks. Well, thanks for your attention. Yeah, thanks, Maxim.